So welcome everyone. It's my pleasure to introduce our seminar speaker today, Dr. Eli Ben-Michael from Carnegie Mellon University. Eli is an assistant professor in two places, Departments of Statistics and Data Science, and the Heinz College of Information System and Public Policy. He does a lot of interesting research that focuses on developing statistical and computational methods to solve practical public policy issues. And so with an emphasis on combining statistics, optimization, and machine learning to develop credible methods for causal inference. Happy to have you here. Please take it away.
All right, thanks. Well, yeah, I'm really excited to be here and to talk with you all about this work. Everything I'm going to talk about is joint work with my PhD student Victoria and my collaborator LP. As a small plug for interdisciplinary work. Yeah, my collaborator LP, he's in the Language Technologies Institute at CMU, which is essentially the Department of Natural Language Processing, although he might not say it that way. And if anyone tells him that I said that, don't, you know. And this is a really interesting set of projects, I think, where we got to deal with what I think are really interesting statistical problems, and I hope you agree, but in a way that leverages a lot of the kind of modern generative AI and language technologies types of tools that exist now. So this is one of those, like, by our powers combined, we got to do something interesting, I think. So I'll be talking about text experiments, and to kind of ground us, I want to give two examples of what I might think of as like archetypal text experiments. So for the first one, this was started in 2019, where if you remember, there was a series of pro-democracy protests in Hong Kong, and the researchers were interested in understanding what causes support for the Hong Kong protesters for people in the United States. And in particular, they had this question about whether mentioning a particular treaty commitment that the United States made to Hong Kong in the 90s would change how people supported these protests. So the way the experiment worked was these researchers went and combed through some congressional speeches, and they pulled out a few different key themes. For instance, they had this treaty commitment theme, but also themes from the speeches, such as talking about the bravery of the protesters or the fact that they were carrying American flags. And for each one of these themes, they wrote a series of vignettes, so basically sentence-long texts that tried to touch on these different themes. And for each one, they wrote many different versions of this. For instance, they wrote over 100 versions of this commitment vignette. So the way the experimental design worked was someone would walk in, I mean, like virtually, and they'd be assigned to some series of these, what they called latent treatments. For instance, the first person might be assigned to commitment, bravery, and economy. And now for each one of these treatments that they were assigned to, they were then sampled a random vignette. So for instance, this person who was assigned to the commitment treatment was then shown a random vignette from the commitment bucket that said something along the lines of, 27 years ago, Congress passed a bill pledging to preserve Hong Kong's special status. Okay, and the same things happen for these other treatments. Now, when the next person comes in, they might have been also assigned to the commitment treatment, but now the flags treatment or the economy treatment. But even though they're assigned to the commitment treatment, they were shown another vignette. So here they're shown something that says, during George H.W. Bush's administration, et cetera, instead of 27 years ago. And the idea here is that by having many different versions of the same concept, they could maybe get at the effect of whatever this commitment treatment is. Okay, so this is experiment type number one. It's super structured. For a second type of experiment, we can think about something that's way less structured. And for this, the question that the researchers had was, what causes text to be perceived as hate speech? And instead of writing a bunch of vignettes that maybe borderlined on hate speech, instead what they did is they scraped some things from the internet. So basically, they went to the kind of dodgier corners of the social media site Reddit, and also this other social media site Gab, which from my understanding is for people who are banned from other sites. And so they scraped a bunch of these comments that were, maybe looked kind of odd. And then what they did is they would bring someone into their experiment and they would show them a random comment from this pool. So I'll just warn you, I'll have starred out profanity here, but hopefully we'll be okay. So for instance, the first person who comes into the experiment might be shown this comment, right? It's refreshing when you see a business call out someone on their BS. Okay. So now after the fact, we can look at this comment and say, well, all right, there's profanity, right? That's the thing that we're interested in. But there's also something else in here, right? This is actually expressing a measure of surprise, right? Okay, what about the next person who comes in? They might be exposed to a different comment from someone who really hates the TSA. And here there's profanity again, but there's also other stuff, right? There's aggression, right? This is kind of a much meaner comment. And also it talks about like air travel, for instance. Then finally, someone else who comes into this experiment might get something totally different from someone who doesn't like pumpkin spice lattes. And here there's no profanity, but it's also totally different from all those other comments I showed you, right? These are kind of generic and really not offensive to anybody, right? So here in this unstructured experiment, the question is, what is it estimating about the effect of profanity in this case? So what I want to focus on today is trying to understand what we want to estimate from these types of experiments, and then what are we actually estimating? And if they're not the same, how do we make them the same? The key methodological challenge with trying to understand the causal effects of language is that text and language is very high dimensional. There are many different ways to represent the same concept, right? With many different types of texts. So what that means is that if we wanted to start to measure impacts of individual texts, we need to have really, really large sample sizes, right? Prohibitively large ones. So what we propose to do is to instead measure the effects of text corpora, or distributions over text, where we want to ask, what would the average outcome be for a typical text drawn from a distribution? Now, usually in these types of text experiment settings, we're really interested in understanding the impact of particular language attributes. And when you try to measure the impact of language attributes in the setting, you end up with two different types of effects you could measure. On the one hand, there are what we call natural effects of a language attribute. So this captures the effect of that attribute along with everything else that's correlated. So if we're looking at the effect of profanity, it's bringing profanity and everything else that comes along with it, typically correlationally in the data. As I'll talk about, it's actually really easy to estimate a natural effect from a text experiment, but you can only estimate one kind, particular to the types of correlations that are in your experiment. So as I'll talk about, one thing we want to do is to be able to generalize from this experiment to any kind of set of target corpora or other types of text distributions, where we can start to move these natural effects around. And I'll try to sneak this in here. Actually, this turns out to be really intimately connected to the problem of human AI alignment in large language models, which was kind of a little bit of surprise for us, and we got excited about it, so I'm happy to tell you about that. The other type of effect that you can measure is called what we call an isolated effect of a language attribute. And this tries to break that correlation between the focal attribute that we care about and then the non-focal attributes that we don't care about. And as you can imagine, this is going to be a lot more difficult to estimate, right? In particular, because we need to both approximate this kind of non-focal attributes, the things we don't care about, and then adjust for it. And when we approximate them, we usually have to use text representations, right? And it turns out that you're going to lose information when you do that. So what we do is we characterize that information loss explicitly as omitted variable bias for our causal effect estimates, and we characterize the sensitivity of our results to that omitted variable bias. Okay, so that's where we're going eventually. First, I just want to get at this question, though, of what do we actually want to estimate, or what I would argue we want to estimate. And before I do that, I just want to really briefly kind of talk about why we want to run text experiments in the first place. So if we were to look at this hate speech example, for instance, and if we just went online and tried to find comments that were flagged as hate speech, we end up having a selection problem. So like I don't hang out on weird parts of the internet, so I'm not exposed to things that are borderline hate speech very often, but I'm also probably more sensitive to hate speech than someone who is on this social media site Gab, who's exposed to a lot of content like that and probably doesn't think a lot of it is hate speech, right? So the reason why we run a text experiment is to break that dependence between someone's background characteristics and the type of content they're exposed to, because otherwise, how everything exists on the internet now is that it's all highly correlated. So this is the selection problem we're trying to deal with by doing the experiment. Okay, so now as a bit of a warm-up, I want to talk about how we might do an A/B test for two different texts. So say, for example, we want to know the impact of green text versus an orange text. So this is something like message testing or something. So we know how to do this really well now. I'm going to use the language of potential outcomes. So the way we would do that here is we would say everyone has two different potential outcomes. What would happen if they were exposed to the green text, and what would happen if they were exposed to the orange text? And then we'd want to measure the average treatment effect, typically, right? So this is to say, if everyone was exposed to the green text versus if everyone was exposed to the orange text, what would the difference in average outcomes be? This is typically what we want to estimate in an experiment like this. And then to estimate it, it'd be really easy. All we have to do is randomly assign individuals to either get the green text or the orange text, and then just compute the difference in means. We look at average outcomes amongst people assigned to green and average outcomes amongst people assigned to orange. And obviously, this can get a lot more complicated and interesting in terms of analyzing randomized experiments. Okay, so that's when we have two texts. But the problem, of course, is that text is high dimensional. There are many different types of texts, right? We might want to compare, different shades or flavors of the same idea as in that first experiment that I was showing you. But, quickly we have a high dimensional kind of intractable problem. So just in terms of formalism here, in terms of thinking about potential outcomes, now I'm going to characterize every individual as having a potential outcome function, which means everyone has a potential response to every particular text, maybe in their language, right? So for some individual, maybe if you show them the green text, they have a positive response, but if you were to show them the blue text, they'd have a negative response, or the brown text, they'd have a positive response, right? So everyone has their own potential outcome function in this case. Okay, that's a bit of formalism, but what you might say is, okay, well, I think I know what to do here. I'll fix a certain number of texts, and then I'll do a multi-armed experiment. I'll randomize exposure that way, and then maybe I'll do all pairwise comparisons. This runs into two problems. The first is just a sample size problem. So the number of pairwise comparisons is going to grow pretty quickly, and especially if you want to do a multiple testing correction, you're going to run out of power very quickly. But more importantly, I think these types of pairwise comparisons aren't actually that interesting, right? Like practically or scientifically usually. So what we propose to do is to instead think about measuring the effects of text corpora or distributions. I'll be using those two words interchangeably here. And the way this works is you have two populations. First, you have the population of individuals that you want to study. And then second, you have a population of texts that you want to study. And this is what I'm calling the corpus or the distribution. And the way we build up our estimand is we start by taking one individual in the population, and then we take a random text, and we say, okay, what would that individual's response be to that particular text? And then we fix that individual, and then we pull another text from the corpus, and we say, okay, what would that individual's response have been to the other text, right? And we can keep pulling random texts like this. Then we move on to the next individual in the population, we expose them to a random text, right, and so on and so forth. So formally, what we're trying to do is we're trying to estimate the average outcome if we took a random or typical individual and exposed them to a random or typical text from a particular corpus. So I'll be calling this corpus P to mean it's like a probability distribution over text. Okay? So again, the idea is I fix the individual, I pull a random text, I measure their outcome, I pull a random text, I measure their outcome. The flipped version of this is to say, for every possible text, we ask what would the average outcome be, and then we aggregate according to this distribution. All right. No one's yelling at me so far, so I guess we're good.
So just
Oh, yes, perfect, yelling.
I'm going to give multiple texts to each individual.
Yeah, sorry, this is defining the estimand. If we could, we would take everyone and show them, a million of the random texts. Yeah, exactly. Okay, so what this lets us do is compare and contrast text distributions rather than individual texts, right? So we can think about a treatment distribution and a control distribution. And if those two different distributions or corpora are meaningful, then we can actually interpret this effect. As of right now, I have given you no reason to even think this is possible, but I'll come back to that in a second. But I'll just say that doing this kind of thing, taking this randomized aggregate over text instead of looking at individual ones, helps deal with all these kinds of overlap and sample size issues, because now we've really turned this problem back to a binary comparison instead of having this high dimensional comparison. And this kind of thing, where you take a randomized aggregate of something high dimensional or dynamic or continuous, is often called a stochastic intervention, and it's an idea that's been kicking around in the literature quite a bit. So what we're doing is we're applying that idea to the impacts of text. Okay. So how do we define the kinds of contrasts we want to make? So if we go back to this kind of structure, we've gotten rid of any kind of selection problem, right? So now we're just saying a text impacts someone's outcome. And what we do is we represent that text as consisting of two parts. First, there's a focal language attribute. This is the thing that we really care about measuring the impact of. And then we have a series of non-focal language attributes. And both of those things impact the outcome. So, for example, if we go back to this hate speech example, the focal language attribute might be profanity, right? And this is something you could just literally look up, right? You can do a keyword search in this case, but it could be a little bit more complicated than that. And the non-focal language attributes in this case would be things like, does the comment express aggression or surprise or so on, as I was showing you before. I'll come back to how we actually operationalize this later on in the talk, but for now we just think about these as these concepts. Because we're trying to just sort of think in principle, what is it that we want to try to estimate? Okay. Yeah. Of course. No, please.
So now that you've gotten to the point that you have basically random text that you provide to individuals, so you have the whole distribution of text.
Yeah.
Is there a reason to still consider sort of binary situation versus like distribution 1 versus distribution 2, and not sort of some other summary of that distribution or sort of distribution?
Yeah, so the reason why we're thinking about the binary case is specifically because we're thinking about one particular type of attribute, right? We want to care, like, is there profanity or is there not? We could generalize that to think about, kind of continuous style treatments, other things like that.
And the reason I'm asking this question is that profanity presumably is not, like, a lot of things are spectrum.
Yeah.
They're not sort of binary.
Yes.
That's why I'm asking this question.
Yeah. So in principle, everything I'm going to show you, we could then apply the kind of continuous treatment style arguments on top of this. We haven't done that yet, but I don't think there's any reason why you shouldn't be able to do that. Yeah. So you can even think about this as a derivative, right? A difference, you can instead think about like a derivative along some continuous scale. The estimation is going to totally change, but the identification won't. Okay. Other questions? All right, well, this graph is not particularly honest, right, though, because there's not this clear separation between these two things, right? There is this connection where, for instance, things that are aggressive might have more profanity in them, right? Or things that have expressed surprise might have more profanity in them. So this connection between these focal and non-focal language attributes is going to be the key thing in defining our estimands here. So if we want to think about measuring the effect of a binary attribute, right, we can just define two distributions, one of which that attribute exists, one of them that attribute doesn't, if we're thinking about binary ones. But to continue to define these distributions, we need to say something about the non-focal language attributes. And this is where we get into this distinction between these two different types of effects. So first, we have these natural effects where we keep this correlation between the focal attributes that we care about and then the non-focal attributes that are sort of ancillary to our study. Formally, what we're saying is that under the treatment distribution, the distribution of the non-focal attributes just follows the observed conditional distribution for when that attribute exists. So we're saying, anger, surprise, all of those things are just following the conditional distribution that we can observe in the data when there is profanity. And in the control case, it's when the attribute doesn't exist. You don't actually need to specify any of these things, but this is more just, again, to say, in principle, what are we trying to estimate? The other thing then we could try to estimate is this, what we call, definitions. Right now, I'm just saying, trying to define what we could, in principle, try to estimate. I haven't said anything about how we're going to do that. That'll be next. Yeah. And that gets even worse for when we think about what we call isolated effects, where we want to break that correlation, where what we're trying to define here is that the distribution under treatment for the non-focal language attributes and the distribution under control are the same. And like they're just going to be maybe, in this case, the marginal distribution in the data. So if we go back to this hate speech example, what this is saying is if I take a typical comment and I add profanity to it for the typical comment, what would the effect be? And this again, in principle, is breaking that correlation, but the context still matters because the typical comment, for instance, was going to change depending on what social media site you're on. Yeah.
I'm going to read a question on chat.
Sure.
I have a clarification question. Can you clarify how you go from unistructural data to the structured attributes, or unstructural data, unstructured?
Yeah.
To the thank you. To structured attributes.
Yeah. So this breakdown, right? So right now, I'm actually going to totally punt on structuring the non-focal attributes because, as we'll see, when we think about natural effects, we don't even need to characterize these at all. We have to say anything specific about them. For the focal language attribute, that is something I'm conceiving of. Some people call this a codebook function. Like this is something that you as a researcher are already deciding. It's something computable from the data directly. So something you could, in principle, read off a text, but it's still a function of it. And I'm going to come back to this part. I guess whoever's on Zoom can't see that I'm pointing. But I'm going to come back to this part about the non-focal language attributes when we talk about isolated effects. I hope so. If not, wait like 20 minutes and then tell me if I didn't answer the question. Okay, so these are just definitions, right? In principle, the two things we could try to estimate. So now what I want to do is talk about estimating these two things, first starting with natural effects and then going to isolated effects. Okay. So let's start with these natural effects, again, where there's this correlation between the focal and non-focal language attributes. So these are super, super easy to estimate from an experiment. The basic way you do it is you just start with some experimental corpus, right? These are some series of texts that you already start with. You randomly assign texts from that corpus to individuals. And then after the fact, you can use your little codebook function and just say, okay, amongst individuals that saw text that have the attribute, what was the average outcome? And amongst individuals that didn't see it, what is the average outcome? And then you can just take the difference in means. This is exactly what that hate speech example is doing. That's how that experiment worked. And what that's doing is it's estimating the natural effect in the experimental corpus in particular, right? So amongst the data that you have and the correlational structure that exists in there, what is this natural effect? So that's all well and good, but oftentimes we don't just care about our experimental corpus, right? We care about other types of text or other types of distributions that we didn't randomize over. So for example, in vignette experiments, like in the first example I showed you, those texts can often be quite artificial, right? And not have correlational structures that exist in natural text. Or even in, for instance, the hate speech example, they only looked at 2 social media sites, but the context could be different in other social media sites. So in some ways, this isn't really a problem, right? You could just run a new experiment on this new distribution, but that costs a lot of money. So what we propose to do is to transport or generalize from your experimental distribution to your target distribution using these ideas from generalizability. The way this works is how you might expect using kind of inverse propensity score weighting style identification, where basically you can just say that show that the average outcome, if someone was exposed to a random or typical text from the target distribution, you can just get that directly from your experiment by taking a weighted average of the outcomes in your experiment, where we weight each individual and each text that they've seen that they're shown by the ratio of how likely it is for that text to show up in the target distribution divided by how likely it is for it to show up in the experimental distribution. Okay, so in principle, the denominator here is known. We design in our experiment the probability of ever showing a particular text. Like if you're randomly choosing amongst texts, it would just be 1 divided by the number of texts. So what we need to specify then is what our target distribution is. In principle, if you can write out a probability distribution over text, you can do this. Now, that can be difficult, although I'll show you in a second that it's not that hard anymore. But one easy way to do that is to say, specifically, I want to use an existing corpus of data and say, what if I had run an experiment using that corpus? To do that, you can just build a little classifier where you paste together your experimental corpus and your target corpus, and then you build a classifier that classifies which one it's in. And then you can show, just using kind of Bayes' rule, that this density ratio, this ratio of probabilities, is just proportional to the classification probabilities. Okay, and this is kind of standard inverse propensity score weighting style estimation. Okay, we also tried doing some crazy, wacky stuff, pulling out the generative probabilities from an LLM, which sort of worked, but in the interest of time, I won't actually talk about it. And we did some validations, but actually what I want to focus on here is an application of this to LLM alignment, because this is a case where actually we can specify a distribution over text. So let me give a really brief sort of blitz through how LLM alignment works. And this isn't actually my area of expertise. This is more of like a way that we found using causal thinking can be helpful. So large language models are trained on these kind of giant data sets that exist, everything that's ever been written that's on the internet ever, right? And if you want to use a particular task, you want to use this for a particular task, usually you have to do a fine-tuning step. So it starts generating texts according to the particular domain that you're interested in. So that's the first step. And then the second step is usually to have some kind of alignment to make sure that this LLM is generating texts that align with human preferences, that people like, or that have some kind of outcomes that we care about. Existing approaches to this type of alignment don't really think too carefully about correlation versus causation. And in particular, they run into issues with this type of selection issue where the kind of content you're exposed to depends on your background characteristics. So kind of formally, the first thing we're arguing is that you should try to find texts that cause a desired outcome, right? That's kind of the alignment question. Okay, we're saying, how can we generate text according to some distribution that'll lead to the outcome that we want, causal? Okay, so the second component of this then is to notice that a language model is actually a text generation machine, right? It actually induces a distribution over text that you can actually read off, right? That any of these LLMs will give you token probabilities. You can just say, here's how likely this particular string of text is. So what that means is that we can just plug this into what I was just talking about transportation, where we can say that the value of a language model F is just the average outcome under the distribution generated by that language model, which gets us back to where we were before. Okay, I'm going to pause here for a second because this is kind of the conceptual point. We're saying if you could draw a bunch of text from an LLM, which you can just press the button again and again and again, and you were to expose a person to them randomly, what would the average outcome be? So for instance, hate speech, as we'll talk about in a second, we don't want hate speech, right? So what we would do is maybe have our outcome be no hate speech. And we'd ask, if we were to draw texts from this LLM, how often would someone perceive it as hate speech? And we'd want to try to minimize that. Okay. So the key here then is that if you've done an experiment, like a text experiment as we talked about, then this question of estimating the value of a language model is just the same thing as transporting to a new target distribution. We're now, instead of saying, hey, I have some existing body of text that I'm trying to say, had I randomized with that, what would have happened? Now I have a machine that generates text, and I say, if I were to randomize with this machine, what would happen? Now, again, you could run an experiment to do this with the machine, but it actually becomes difficult then to sort of update the machine in process. So instead, we show how you can just use the experiment itself to get at this. So we call this causal preference optimization because every LLM alignment thing needs a name now, I guess. But the basic idea is to just do what I said before about using the density ratio. So to estimate the value of a language model, we go into our experiment and we weight the outcomes by the ratio of the probability that the language model would generate that text divided by the probability that that text showed up in our experiment. Okay, so this will upweight texts that are more likely to be generated by the language model and downweight texts that are less likely to be generated by the model. Yeah.
Experiment might have a different support.
Yes, so this is a good point. So the question is that your experiment could have a totally different support than what your language model is working on. Yeah, it could have a smaller support. So this is actually a very subtle question about overlap, where you have to assume essentially that a representation of the text, there's still overlap. That's one way to think about it. The other way to think about it is actually the first thing we do is we fine tune. So we actually restrict down to a domain that this is believable, right? That we pulled some random text from a corpus, right? But if you fine tune onto that same corpus, then the support is the same. Now, in principle, the language model can generate new things that it's never seen before. You can think about that as interpolating, right, amongst what's in that experiment. Did I answer your question? It ends up being actually even more subtle than that, but I'm going to talk about that in Q&A. Okay. So the benefit of this is that it doesn't require us to fit any models, and everything is known, right? We know the probabilities of generating the text, and we know the design probabilities in our experiment, so everything is unbiased and everything is great and dandy. The other thing we try to do is to try to use an outcome model to do a double robust version of this. What this means is if we get a predictive model that can take in a text and predict someone's outcome, we can then use this to try to more efficiently get at the value of this language model. So what we do is we say, first, we take our language model and we say, if we generated text according to this language model, what would the average predicted value be? Okay, so that's the first component of this. And then the second component is we go back to our experiment and use it to debias the predictive model. So we look at the residuals, the difference between the outcome that we see and what the predictive model would have predicted, and we reweight those residuals by this density ratio. This is actually just totally equivalent to doing regression adjustment in a randomized control trial. And so what that means is that regardless of if your model is biased or not, this is going to be an unbiased estimate of what would happen if you exposed everyone to outputs from this language model. We show in the paper, I won't dwell on it, that this works just like you would expect from a randomized control trial. By including a model, you can reduce variance. And the more you can reduce variance depends on how good the residuals are. Yeah.
Why is the density ratio known?
Yes.
Know the density for it from the model?
Yeah, so there's two components to the density ratio. The first is the probability under the language model of generating the text. This is known because this is literally computer, like if I fix the model, I can literally compute this by doing a forward pass through the model. The experimental design probabilities are also known. And so that's what we know both components. And actually, I forgot to mention here, I'm just talking about estimating the value, but then you can optimize these by differentiating these objectives with respect to the model parameters. You can like literally put that into autodiff. It kind of works. It gets a more gnarly than that, and I'm happy to talk about that afterwards. But yeah, you can just conceptually just think about it as optimizing this now and taking derivatives. Okay. In the interest of time, I'll briefly talk about an empirical evaluation we did where we just tried to see if whether this works at all. So we took these two text generation tasks that I talked about before. So for the hate speech example, we wanted to generate text that's not perceived as hateful. And for the Hong Kong example, we wanted to generate text that causes support for the Hong Kong protesters. And what we did is we took Meta's open source large language model, and we tried to do these alignment mechanisms, either using reinforcement learning with human feedback, which had to be slightly different in our setting because it was a slightly different setting than it's usually applied, where you can essentially think about that as just using the predictive outcome model. And then we used our approaches. And the way we evaluated this is we would just take a piece of text from either of those two distributions that we were working with, take half of it and ask the LLM to generate complete the rest of it. And what we do is we pit our models against each other, where we say for the same completion, right, which one is better than the other in terms of these objectives. We did this on a small sample of humans, and then we fed this back into the machine by putting this through GPT-4 to get these values. And I guess I'll just briefly say what we found. We looked at the win rate difference. So if it's more than 50%, that means that one model is better than the other at this. And briefly, what we find is that this double robust, for the hate speech example, using the double robust version or not didn't really make a difference, but both of them were better than using other approaches. In the Hong Kong example, interestingly, using the double robust approach, including this predictive outcome model, actually made things worse. And the reason for this is that this Hong Kong data set is much smaller and much more difficult to predict in. So it's a really hard language modeling task. And in that case, it seems like, if we have a bad enough outcome model, it's not really helping us in finite samples. Okay. In the time I have left, I want to talk about estimating isolated effects, but I'll pause to see if there are any questions. Okay. All right, so for estimating isolated effects, it's going to be much more difficult than estimating natural effects, because in principle, we would need everything that's sort of non-focal, the things we don't care about, to be independent of the thing we care about, which just doesn't happen in natural text, right? The whole idea about language is it's all very highly correlated. So there are two potential ways to get at this. The first is to design your experiment well, and this was what this first Hong Kong example was doing, where you can construct or generate or sample text in some kind of smart way so that non-focal attributes that you can measure are independent of your focal attribute. Once you do that, then you can just sort of run through everything like I've shown you before of just estimating differences. The second approach is to take an analysis approach, where what you can do is use naturally occurring text, but then after the fact, try to adjust for the fact that there are these dependencies. But the thing is that both of these options require operationalizing what these non-focal language attributes are. So now finally, I'm going to get to this point. So there are lots of different ways to do this. And just to give a really brief overview of where I see this existing, and the first approach is to take expert designed features. So this is a really qualitative approach where you have a scientist, a researcher read a lot of these types of texts and come up with a code book, right? Sort of pulling out key themes and then going through all of them and coding everything. These are really high quality, and usually they're very relevant to the thing you care about. So expert defined features are like great, but they're also very expensive to make. So the second thing that people often do are use lexicons, which essentially just do word counts. So you take a few predefined or sometimes like semi-automatically generated sets of words, right? You might say there are certain words or word stems that correspond with aggression, for instance, and then you simply count those in your piece of text, and then you do some normalizations because most words don't show up in most texts. Now, more recently, people have just been using language model embedding. So any type of language model, be it large or small, has some kind of hidden layer usually, and that hidden layer is a representation of the text. So people, for instance, using BERT or something, they'll just pull out that representation, and then you get something that's totally uninterpretable, but it's like dense and feature rich. And then lastly, kind of going full circle back to the expert defined features, people have been using LLM prompt engineering to essentially try to do this qualitative thing again, but now at scale, feeding it through an LLM. Okay, so for the moment, let's say we did one of these approaches, and let's say it was the right approach. Okay, so let's assume that we exactly know how to measure these non-focal attributes. Two bits of notation that I want to have because it'll be important later. Here I'm going to be talking about the propensity score and the outcome model. So the propensity score is the probability of seeing our focal language attribute given the non-focal attributes, right? So like the probability of seeing profanity given aggression. And the outcome model is the expected outcome given those attributes. Okay, so what do I mean by saying we know how to measure these focal attributes? I mean that the following three assumptions are satisfied. The first is a consistency assumption, which turns out to be key, which is that if we want to know someone's potential outcome to a particular text, all we need to know about that text are these language attributes, the focal and non-focal. This is a really key and tough assumption, so I'm going to come back to it. The second one is that we have randomized assignment of text. There, we're good. We did that in our experiment. And lastly, we need overlap, which is that they're not perfectly aliased, right? Our focal language attribute doesn't show up deterministically given our non-focal attributes. The overlap assumption, sometimes you can do by design and make sure that you limit your cases to thinking about it. But the real problem is the consistency assumption, which is that our our language representation is correct. So I'll come back to that in a second. But if you have these assumptions, I'm going to show that basically doing this problem, right, estimating the isolated effect of a language attribute, is just the same thing as covariate adjustment for an observational study. So like literally, I just take the problem from this kind of big unstructured thing to a data set where I have as a treatment my focal language attribute, as covariates everything else, my other representations, and then you can just identify treatment effects in the same way as an observational study. It's formally the same problem, which means you can do whatever you want. You like matching, you can do matching. You like propensity score weighting, you can do that. We use, augmented inverse propensity score weighting or double robust approaches, just because that's what people do these days. Okay. So here's the thing, right? This is all assuming that we have the right representation, right? But really, we don't. In practice, we can only ever approximate these non-focal attributes, right? We choose a particular way to represent language using one of the approaches I talked about before, and we don't know if that's actually right? We just have to kind of go for it and see what happens. So the issue, of course, is that by kind of going to this approximated language, right, we might be missing something. There could be things that in our approximated representation that are missing that are in the true representation, right? So these are omitted variables, is how we're thinking about them. And actually, just like doing this isolated effects estimation is the same thing as an observational study, doing covariate adjustment, this problem of approximating language is the same thing as omitted variable bias. Is that a question or? Okay. Okay. So what this means is now you can use your favorite tools for omitted variable bias as well. We use this approach. I guess Carlos isn't here. I was going to gas him up because I really liked this paper. But we use this approach from Carlos and some co-authors where they kind of show how to broadly characterize omitted variable bias across a lot of linear functionals, in which case we have a special case of this where the omitted variable bias can decompose into two terms and then some sensitivity parameters. The two terms are first what we're calling a fidelity term, which is how well the representations capture the observed outcomes. This is literally just the mean square error of the best possible regression using the approximated language representation on the outcome. So the better that is, right, the smaller that mean square error, the less room there is for there to even be bias, right? Because if you can totally predict the outcome, right, in the extreme case, then there's nothing left to have omitted. The second part of this is an overlap term, which just measures how much overlap there is across these representations, across levels of treatment. And this is just the average squared propensity score weight. So this will be much larger if there's a big difference in your representations amongst treatment and control, and it'll be smaller if they're overlapping each other. And the idea here is that the further apart they are, right, the less robust your results are going to be because you can sort of move one thing over to one side and that would ruin everything. I'll come back to the sensitivity parameters in a second, but for now we can think about these fidelity and overlap measures. And what we found is that these fidelity and overlap measures can actually be really useful ways to actually diagnose and understand whether our language representations are working. So what we propose to do is to try to estimate isolated effects across a series of language representations and assess their sensitivity to omitted variable bias by both looking at these measures and then sort of doing a full sensitivity analysis. Okay, I think I'll have time to go through this. So we did this in like this particular uncontrolled setting, which is this wild paper that I thought was really, really awesome. That was about automated causal inference, where what they did is they scraped a bunch of Reddit posts about two different weight loss drugs. And then they sort of did some really sort of thoughtful prompt engineering to extract an outcome from them, which was whether someone lost weight, and then a bunch of other confounding variables. And then they tried to compare that as an observational study to some clinical trial results of the comparison of those two drugs. This is not a text experiment, but it has the same type of structure of what we've been talking about. So what we did is we took this as the focal language attribute being the drug name. So again, this is something you can just compute easily, right? It's a keyword lookup. And then we thought about doing different types of representations for everything else. And here, in this case, that everything else is getting at the confounding question. We tried a whole series of approaches. I actually don't want to focus too much on the actual estimates because everything was kind of noisy. But what I do want to focus on is on these OVB metrics. So we tried doing this LLM prompting that they did, just sort of recreating their approach. We tried two different lexicons, LIWC and empath. We tried two interpretable language embeddings that use a deep learning model but essentially do some sort of like k-means clustering around these lexicons. And then we tried just taking the hidden layer from a particular type of language model, which is MPNet. So what we found, oh, and I'll just say we use de-biased estimates of this overlap and fidelity, so they can be negative, which is a little bit unfortunate. But what we found overall was that in terms of overlap, the language model was really, really bad. Everything else was roughly the same, but the language model was super bad. And this is because it's high dimensional and rich, so you can really easily tell the difference using these features. But if we look at fidelity, which is how well those representations are getting at the outcomes, we found that it was really, really good, but so was just LLM prompt using their sort of careful and thoughtful feature generation. And we combined all of this into the robustness value, which is just saying what value of those sensitivity parameters would you need to have in order to undo your effect. Here we're looking at the point estimates. So here higher is better. And the way this all shakes out is that, and the reason why I'm bringing this up is that this high dimensional dense representation ends up being really not robust. So it actually measures the same, the estimated effect is the same as using this LLM prompt engineering, but the robustness is really, really bad because the overlap. And then we also find that these kinds of interpretable language representations seem to be pretty robust and useful because they kind of hit a sweet spot between fidelity and overlap. Okay. In the time I have left, I just want to briefly come back to this profanity and hate speech example to give you a kind of example of these natural versus isolated effects, then I'll wrap up. So what I have here is, unfortunately, you can't see the grid lines, but you'll have to extrapolate. What I have here is the estimated natural effect of profanity on whether someone perceives something as hate speech overall, and then separated by social media sites. Okay, so I guess I forgot to mention this. This is in some ways a really dumb question, right? Because a lot of profanity just is hate speech full stop, right? So we would expect to see a large effect. That's why I pulled this out, just to have something that was like super robust and large effect. So again, that's what we find, right? Overall, what we're saying is that overall, we find this estimate about 40%, right? Which is to say that among posts that have profanity in them, right, people perceive them as having hate speech 40% more often, percentage points more often. And in particular, we see a difference between Reddit and Gab, where on Gab, that effect seems to be larger. Now, this is just the natural effect, though, right? So this is including all sorts of correlations. So it could just be the case that, on Gab, users use profanity in instances where there's just kind of more other things that are causing hate speech, more often than in Reddit, where maybe people are just using profanity kind of willy-nilly, right? Like that person who, well, I actually didn't have a good example of that, but right, just using it willy-nilly. So when instead we try to get at the isolated effect, here we're using these language. All right. Here we're using these kind of interpretable language models. We see that those effects move down a little bit, but that gap persists. So what this means is if I was to take a typical Gab comment and add profanity to it, there would still be over a 40 percentage point increase in the perception of profanity. And on Reddit, that would be smaller. Now, this could be one of two reasons. One, it could be something about the typical Gab comment being different than the typical Reddit comment, or it could be the profanity that we're measuring, right? So here I'm doing a binary for is there any profanity, but we know some is worse than others and some might be hate speech. So it could be that on Gab, they use those more. Okay. One last thing I want to talk about here is that you can use the kind of existing tools for omitted variable bias even more. So one thing that's really popular is to use these kinds of contour plots where I haven't talked about the sensitivity parameters, but there's two of them. One of them is essentially how much the propensity score with the language representation, the approximation, can predict the true propensity score. And we look at 1 minus that on the x-axis. And the y-axis is essentially how much predictive power is there in the residuals from the language model representation as a prediction of the outcome to the true residuals. So as this goes up, that means that the omitted variables can be stronger. And as this goes up, that means that those omitted variables can be more imbalanced. And what you can do is sort of compute for any value of these sensitivity parameters what the lower bound, in this case on the effect, would be. And you can get this kind of dashed line. But the really powerful thing about this is now, because we can use something like an interpretable language representation, we can do this kind of process where we can benchmark it by pretending we have the right representation and then dropping it and seeing where that lands up. What we find is that when we drop sort of concepts like rage and hate and aggression and anger, that's kind of all down here, but that's not even close to overturning the effect. But again, profanity obviously is causing hate speech because some bad words are really, really hateful. All right, I'm going to wrap up here. I'll just say that the kind of key challenge here of estimating the effects of language is that text is high dimensional. And today I've kind of talked about a framework and some paths forward, but it's like nowhere near kind of the actual sort of end of that story. And I think there's lots of really interesting questions. In particular, recently I'm being really focused on design, right, and how we can think about designing these experiments better. But I'll instead pause here for questions. So thank you. And here's the papers this is based on. Thank you, everybody.
Thank you for the great presentation. I have a question about the Reddit thing on the drawing.
Mm-hmm.
So I was thinking whether that setting matches more of the natural case, whether isolated case, because if you are taking a different drug, you may represent your feelings differently, so the distribution might be different.
Yeah, so that's a great question. We were looking at it as an isolated effect because we were thinking about the comment had the outcome in it too, but once you pull that out, it has what drug you took and then other things that you mentioned alongside that. And the reason why we're thinking about an isolated effect there is we're saying amongst people who mentioned similar things, but one of them said they took one drug versus the other, what was the difference? But we were thinking about that again as like a confounding style problem. But what you're saying is, well, maybe, I mean, this is where this is a kind of tough example. If someone lost weight, they might just be writing about things differently anyway, right? So in some ways, all of this is post-treatment, right? And by doing this isolated effect thing, we're actually conditioning on post-treatment variables, which I think is true, but I guess I didn't really show this, but we actually did compute the natural effect. In this paper, we have to call this the naive estimator because of ML conferences. But what we found was actually that it was negative, right? So if you don't really do any of these types of isolation, on average, people who reported using one of the drugs versus the other reported less weight loss, which was the opposite of what the randomized control trials. Yeah, no, it's a good question.
Regarding this embedding here, so that's like the embeddings can take a variety of different
Yeah. Yeah.
But like really just the trade-off there is like how much information is conveyed or like the degree of overlap. Was there just like a default length you were using, or like how does that play into the high dimensionality versus the overlap constraint?
Yeah, so that's a great question. So in this case, we used just a default length, but we did do a totally different type of kind of validation study. Let me see, do I have it here? Yeah, perfect. Where I won't talk all about the details, but we actually generated outcomes kind of in a fully controlled way, where we used just 10 interpretable features, and we built a model, and then we generated outcomes according to those 10. And then we looked at what happened where we did our representations using just 2 of those dimensions, 3, 4, 5, up to 10. And so here was an example where, again, this naive estimator is if we don't do an adjustment, and then if we start to adjust for those additional features, here was an example where actually if you adjusted for 3 of them, that would have been enough. Did I put the other example? But we have another example, right, where it actually turns out that just adjusting for 2 of them got you close by chance, and then as you adjusted for more, it got you away. And then eventually when you get to, 9 is the correct answer, you get back to unbiased. So it's actually harder to say specifically which direction the bias might be, because sometimes, bias could cancel out, which is what's happening here. But more broadly, we find that if you look at the overlap and fidelity metrics, as you increase the number of dimensions, right, this overlap is getting worse, which is what we expect, but then the fidelity is getting better. And then the robustness value is a little tough to look at because it also includes the size of the effect. But these 2 metrics we find to be really, really useful for that. And in principle, we could do this with the high dimensional. Actually, we should do that.
There has to be composition, overlap, and fidelity.
Yeah. Here.
ATE?
Oh, no, sorry, this is saying amongst cases where the focal language attribute exists, we look at 1 over the squared propensity score. And then amongst cases where it doesn't, we look at 1 over the 1 minus, the squared 1 minus propensity score.
That's not the double robust estimate for ATE?
No, because we're squaring the propensity scores here. Right, sorry, yeah, so it's kind of hidden. So we're squaring the propensity score, so now this becomes a measure of overlap. If there wasn't a square here, this wouldn't be a really meaningful concept, but because it's squared, what that means is now if we have cases where sometimes the propensity is high and sometimes the propensity is low, one of these two things is going to blow up, right? And then that gets you at variability. And actually, if you look at the, this is actually a key component of the kind of semi-parametric efficiency bound right here in terms of these squared propensity scores. So it's a worst case scenario, but it can happen.
Just curious, how do you
Estimate the overlap in fidelity. Yeah, so this is where there's this neat trick, and again, this isn't us, this is from this paper, and Carlos isn't here, so I can't, again, gas him up on this. But there's a debias, so one is a plug-in estimator, right? You can just plug in estimates of the propensity score and get at this. There's a debiased version of this where essentially you can use balancing properties of the propensity score to show that you can estimate part of this on the other part of the sample. And that actually doesn't work all the time. For instance, I'll just note, like, we actually ended up with a negative estimate here. I was hoping nobody noticed because I guess the dashed lines aren't showing up on this. So the debiased estimation is sometimes a little tough, but you could always just do plug-in estimation as well.